we're talking about policy improvement, Monte Carlo planning, and we're going to get to tree search hopefully by the end of the lecture today. And just to remind you, what we did here is we said, well, we have a policy that we are given, and we also have a simulator, and we'd like to be able to improve the policy sort of in online fashion using the simulator. So we're going to use a little bit more time every time step to make a decision, and in return, we hope that we'll do better than the policy we're given. And the idea was really simple. If we were in a state S, these are the actions that we have to choose from. We created these bandit problems so a bandit problem where every arm corresponded to an action. And what these bandits did was basically do a simulation that estimates the Q value of that action for the particular policy. And so if you remember what that looked like, basically every time you pulled an arm, it would generate one of these trajectories. And this was take action A1, follow policy pi, and it would return whatever the sum of the rewards was along that path. Discounted sum if you care about discounting. And then a bandit algorithm will try to find the arm that has the best expected value, which is basically the best Q value. So that's basically what we did, and we said that this will essentially simulate doing, it's like if you started with a policy and you did policy iteration for one step over the entire state space, and then you took the action that you got just in state S, this simulation approach is going to try to give you that policy improvement action just for state S without doing it for the entire state space. So it's kind of a neat little trick. You're doing policy iteration, but only where you end up in the world. So yeah, this is what it kind of looked like. We've gone through all this. And of course, you can use other bandit algorithms. We talked about that. This was a non-uniform bandit algorithm. And then you could do multi-stage. That's where we ended up. So, and what we saw was that if you're doing multi-stage, that means you're doing policy rollout on the policy rollout policy. And essentially what that meant was this is our bandit problem, but each one of these dots has to figure out what the policy rollout action would be for this particular state, So you have to do all the work in that simulation tree for every one of these dots. And so basically, if you want to simulate multiple stages, you are going to have to pay sort of an exponential price for each stage that you want to go to. So, I don't know, was this concept understandable? A lot of people have trouble with this. But effectively, these simulations here are of the one-step policy improvement policy. Right? Each one of these simulations, and that requires a full Monte Carlo rollout to figure out what each of the actions are. Right? And basically, we went through this example of solitaire where some people had done some work. They started with this naive base policy, just a simple rule-based policy, and they applied multiple stages of rollout to eventually getting pretty good performance, a lot better than the human. And so that was a nice example of where you don't put in a lot of thought into your base policy, and you could have spent months trying to improve that base policy by including more rules. But instead, you have a simulator, and you don't do any thinking at all, and you just do multiple rounds of rollout. All right. So we can there's a lot of places where you can write mediocre policies and you get good gains. I've seen this applied in lots of domains, and these are just a few. Like compiler instruction scheduling. Those of you who might have dealt with this, basically, there's all kinds of heuristics for scheduling sort of the instructions in compilers, and you can use policy rollout for that to make the scheduling decisions. So any questions about this? That's basically policy rollout, nice little tool to have in your back pocket. So the other type of policy improvement approach that I want to talk about is called policy switching. And this is motivated by the idea that, well, in a lot of domains, we might have many policies available to us. Right? There's a whole bunch of research fields that essentially study coming up with different types of heuristic policies to solve problems. So I just mentioned compilers where they have instruction scheduling heuristics or policies. There's a whole industry where people come up with different ones. And they're competing with one another, trying to show that this one's better than this one. In reality, it's usually the case that, some are better in some places and others are better in other places. There's like no dominant strategy. And so, same thing in networking. Networking research, there's a lot of work on the empirical side, developing different policies for serving packets, dropping packets, scheduling packets, routing packets, and who knows which one's better, right? They're all competing. They're trying to show simulation results. And the reality is usually there's not any single best one. It's just this one's better over here, this one's better over here. So you'll come into a domain and there might be multiple policies. And we don't want to necessarily have to choose which, just one of those to improve. That's what the policy rollout approach that I just showed you would have to do. You have to give me one policy and then I'll improve it, but how about all these others? The other thing that can be a problem with policy rollout, as we showed it, was the most basic version is going to scale in terms of the number of actions, right? And so if you have a gigantic number of actions, you're going to have trouble. And gigantic numbers of actions often arise when the action space is combinatorial in some way. Like you think of it as there are many buttons that you can press, and the different combinations of buttons constitute an action. It can arise in other ways as well. And so this could be pretty expensive. It scales in terms of the number of actions, and so you might want some way around that. And that's both of those issues is something that policy switching can help you deal with. So policy switching, what we're going to do is we're going to start out assuming that we have a set of policies. So pi 1 through pi n. And we're not going to care how these are implemented. So if the underlying state space of the MDP has a large action space, we're not going to care about that. We just assume that these policies have a way of, if you give them a state, they'll return an action. So they could be implemented in any way that you could imagine. And what we're going to assume here is we have these policies, and generally we're going to think of different parts of the state space. One of the policies might be better than the other. And it's just we don't really know which policy is best. So there's no rational way of choosing which one to follow at any one time. So that's sort of what we're thinking about here. And policy switching just gives you a very simple way of using simulation to basically switch between policies in a way that you're going to hope is better than just sticking to one policy. And that's in fact, the theory at the end of this will basically tell us that through this policy switching procedure, you're going to be guaranteed to do as well as the best policy in your set, which is a pretty interesting guarantee. So you give it a whole bunch of policies, and this is going to do as well as the best one in the set, if you had known that at the start. We'll talk a little bit about that later on. It does not say that you'll do as well as the best way of switching between policies over time, but you'll do as well as the best single policy, if you could do that. All right, so this turns out to be relatively straightforward as well to turn it into a bandit problem, right? And the way that we're going to do this is effectively we're going to have an arm for every policy. Okay, so we're in a state of the world, and we want to select an action. And so what we're going to do is we're going to define a bandit problem where there's one arm for every one of these policies. And we're going to use the bandit to basically try to figure out quickly which policy is best in this state, right? And we'll see that that's relatively straightforward. Which policy is best? Well, you could simulate you could simulate a policy many times from that state, and the average of those simulations will be the estimate of its value in that state, right? And then you could do that for every policy, and the best one would be the one with the best average value. And a bandit algorithm will try to give you a way of finding that quickly, like more quickly than just doing uniform sampling. So that's what this sim function is. So this is just a randomized function that we implement with our Monte Carlo interface, right? All you need to do to implement the sim function, which is just going to simulate pi for h steps, or pi I in this case from S. All you need is the function that returns the next state given a state in action and the reward. So these are very simple functions to implement. And once you do that, you can define your bandit problem. All right. So what we're going to do is basically, so this is just showing you the uniform bandit. So what we're going to do is basically, find the best policy, and we're going to take the action that the best policy says to take in that state. We get to the next state, we find the best policy, we take the action that that policy says to take in the state. Okay? And this is showing you the uniform bandit approach where you're sampling the policy the same number of times, but you could use any bandit algorithm you want here. So let's just make sure we're all on the same page. So again, this is our real world experience here. We're in state S. We form this bandit problem, do all our simulations, and it says, oh, pi 2 is the best policy. So in the real world, we take whatever pi 2 says to take in S, right? And we keep on doing that. We end up in a new state, and we do another bandit problem. We say, oh, pi k is the best in this state, and we take the action that pi k said to take in S prime. Okay? So it's really pretty straightforward, and you can see why it's called policy switching. You're just, at every step, you get to choose which policy to follow, and so you're not necessarily following a single policy throughout the trajectory. All right? So any questions about how this works? Right? It's yes.
So because each policy can be stochastic, so actually for each one can be like actually there's a lot of actions you can choose from as well.
So we're not assuming anything about the policies really. We're just assuming they map states to actions, and they could be stochastic as well. They could be stochastic policies, but they don't have to be. But these trajectories in general are going to be stochastic because of the state stochasticity, the transition dynamics, the reward stochasticity, and we're in this section we sort of have a randomized reward function that returns a distribution, and also if your policy is stochastic, that could even add more to the randomness here. So lots of room for randomness, and that's why you've got to do. That's why we try to use bandit algorithms to try to find out the best arm quickly. Right? If there was no randomness, you would just simulate each policy once, and then you would know which one was best. Right? There would be nothing really interesting to do there. Right? So any other questions? Yes.
Also, instead of executing the policy system, every state can we kind of exploit the state space so that we know that we need to switch at only these states and we need not switch it at certain states, something like that.
So you mean try to characterize where each policy is best in some
Yeah,
way?
at least classifying or grouping them. So for these group of states, we will need this policy, and for the other group, we'll need another policy. So we change. We need to check for switches only at the
Yeah.
intersections or the transitions. So just have a bit higher state, more abstract state representation, which from which you can get that.
Yeah, if you have that information, you could. I mean, you can definitely vary what policies are available at each time. Yeah, what you'd be able to say about that, I'd have to think about. But I mean, the other thing you can do is you could. I mean, you can use this as a way of generating training data as well for making those decision boundaries. And in fact, you could try to learn, sort of you might call this a meta policy that selects between these quickly, so you don't have to do all the simulation, right? That would be a very natural thing to do. Anything else? All right. Let's see. So yeah, number of simulator calls, that's fairly straightforward. We've looked at these diagrams a lot. So these algorithms are dominated by the number of times you have to call the simulator, and also whenever you do that, you have to call the policies as well. So basically, we count the number of dots to know what the number of calls are, and that's going to be, you have m policies. Each policy you're going to, in the uniform case, simulate w times, and then you have they're of length h. So there you have it, MHW, independent of the number of actions, of course, right? Because the number of actions is sort of being dealt with inside each policy here. Somehow, if there's a giant action space, even if it's a continuous action space, these policies just have to be able to deal with that. And so, if it's a robotics domain, this could be a type of continuous state space controller. And these could be different forms of those controllers, or controllers that assume different types of dynamics. So yeah, there's a lot of variations here that you can work with. Yeah, of course you can do epsilon greedy policy switching by using epsilon greedy as your bandit algorithm. That's probably what you would want to do in most cases. It would be more efficient than uniform. And now, so finally, at the end, we like to know, well, is this, at first it feels like, maybe by switching between different policies, maybe you won't do as good as any of the policies because, you follow this policy for a while, and then, it may be good because it was expecting something in the future, but then you switch away from it, and maybe somehow things get worse. But it turns out that that's not the case. This simple switching strategy, as long as you can estimate the value of the policies, works out in the sense that you can state this. You can say that for any state S, the max, so this, if we look at the value of each policy in that state, this is the best value that you could get if you restricted yourself to these policies. That's less than or equal to, this is the switching policy. So pi ps, that's the policy switching policy, the one that's doing all this simulation and finding the action that the best policy in S selects. The value of that switching policy is at least as good as the value of the best policy in our set, right? So that's a pretty strong statement because now, if there's a research field that has lived for a long time by people create different policies and strategies for whatever problem they're interested in, whether it be network routing or whether it be compiler scheduling, you can throw all of those into this set, right? And you're going to be guaranteed to do as well as the best one. So it's pretty interesting that you can actually say that. And this statement, of course, assumes that you can evaluate the policies exactly. So the simulation sort of tells you exactly which one is best. We're not going to go into it, but you can if you assume that you only approximately get the best one, you can add some epsilons over here, and things will work out. So approximation can be worked into this as well. It's just a little messier. Right? So any questions about this statement and what it's saying?
Let's follow up on what you said. Will it not depend on how many rollouts we do and as that the approximation accuracy?
So the whatever approximation. So if you were trying to get a bound on the approximation accuracy, you'd have an epsilon and a delta, and that would depend on the number of rollouts as we've.
Should that not affect the theorem?
So any form of, so this theorem assumes perfect evaluation. So it assumes infinite trials, you could say, infinite simulations. And so if the ability to pick the max policy, if that's approximate, like you pick something that's within epsilon of the max, then you're going to have to add a certain epsilon term here. So it will be an approximate guarantee at that point.
I mean, if we're assuming best simulation anyways, then why does it not say to me that my PS will do as good as any combinatorial of the given space policy? Like it's telling me that it will do as best as one policy, right?
As
Not
the
as
best
it
policy,
has any choice of policies in any states.
it will do. So we give it a set of policies, and our guarantee is only with respect to that set.
Yes. So, for example, let's say the best policy is choose policy 1 in state 1 and choose policy state 2 in choose policy 2 in state 2, right? So,
Well, that's the best switching policy.
yes, that's the best.
Right, so we're not going to do as well as, we're not competing with the best switching policy. We're just competing with the best policy in our set. Right. So if you were to say which policy in hindsight in state S is best, which of our base policies? So let's just say base policies. Like let's say it's pi 2. We're going to do as our switching policy will do as well as that.
Yeah, my question was why can it not guarantee me that it will find the best switching policy if I'm even.
So you mean do as well as like the best sort of switching comment? Yeah, so we'd have to get into that, but you'd have to simulate all the possible switches as well. Right? So we're not, this algorithm doesn't even consider switching. Right? When it's doing its simulation, it never considers switching within one of these rollouts. So if you look here, so these simulations, you're just following a single policy in each of these. And it's looking at that till the end of the game. And to be able to compete with the best, I mean, if anything, like practically you would try to compete with the best policy that switches once or twice, like a bounded number of switches. That would be a natural thing to do. And yeah, you can formulate that pretty easily. But then you would have to be looking at those different combinations when you're actually simulating. There might be some ways to do that more quickly, but yeah.
So it would be something like go-hop rollout if I wanted to have switching inside.
Right. Because if you think about it, if what you're saying is correct, right? So what I could do is okay. So let's say what you're saying was correct. Like we would compete with the best. So I'm just going to give you a policy that. So if there are n actions, I'm going to give you n policies. Each policy just selects each action always. And then, like if what you said was correct, we would converge to the optimal policy because that's the optimal switching. Yeah. So we're definitely not doing that. Yeah. So this guarantee is good when you expect there are policies that are generally good in your space. If you expect that there's policies that tend to only be good in little regions, like if you think of these policies as just macros that operate over short periods, then this guarantee is not really that useful. So we're thinking of like a full policy for network routing, or a full policy for instruction scheduling. And I'll show you one in power systems in a moment as a demonstration. So any other questions? Mm-hmm.
So, in respect of the approximation, do we have the guarantee that if we can do the simulation infinite many times, then we are converting to the truth with a certain rate or something?
Well, this theorem basically is assuming infinite simulations of of a single policy. So if you have infinite simulations here, you're gonna converge to the value of that policy.
We are assuming that we have an accurate enough simulator as well.
Oh, so we're also assuming here we have a perfect simulator, right? So if you assume that you have error in the simulation, then that has to be brought into the bound as well. And you can do that. Yeah, I mean, usually it's sort of based on the max, the max. You look at the worst case error anywhere in the model compared to the simulation, and that's the epsilon that you would have to add in. So you can do that. Yeah. Anything else? All right. So this is a fairly easy proof to go through. So we'll go through it quickly. And basically the proof here basically hinges on this little proposition, which is useful from time to time. So what it says is that if you have a value function, and remember this is the restricted Bellman backup. It's doing one of those policy evaluation iterations. So the restricted Bellman backup basically just takes the reward plus, what do you get if you follow that policy, and then you get value v after that. So if you can show that you have this monotonic property, that this value function, if you put it through the restricted Bellman backup for policy pi, it has this monotonic property, then you can say that the value of pi is at least as good as v. So that's a pretty nice statement to be able to say. This is a very easy thing to prove. So if you basically if you just have v, we've basically been through proofs like this before. So if you start with that, that's our assumption. Well, we know that the Bellman operator, you can apply it to both sides, right? So you can apply it to both sides. So now we have v pi, 2 applied twice to v, right? And now we can have the Bellman operator I applied to v, less than or equal to v pi I plus 1 applied to v, right? So we can derive this chain. And so that means that v is less than, just chain these inequalities, v pi k, v for any k. Right? And the limit as k goes to infinity, if you just keep applying this operator for any v converges to v pi, right? So it's a pretty basic statement, but it's useful to just break it out this way. So we can use this to pretty much directly show that this is true. And so what we need to do is, if we can show that max v pi I here is less than or equal to the Bellman backup operator with respect to the policy switching policy applied to the max. If we can show that this is true, then we've shown the desired result. And so that's all we want to do, right? So for our case, we want this to be the policy switching policy, and we want this to be the max value function, right? So again, you can, and I've simplified notation here to make this manageable. So I've assumed the reward function is only dependent on the state and that it's deterministic, but those extensions just make it bigger. It's not fundamentally different. So we want to prove this here, because if we prove this, then we've basically proven that this value function is less than or equal to the value function of pi ps, according to the previous proposition. So we'll start by writing down this right-hand side. So we write that down for a particular state, and this is just the definition of the backup. And now we can say that this is greater than or equal to this next line. And so all we've done is basically replaced PS with I star as the index of the best policy that would have been selected in that state. So this is replacing it with I star is not a big deal, but we took the max outside of the sum. And so this, so if you have a max inside the sum, you can maximize for each individual state that you come across. Whereas here you have to find an I that sort of works overall for the state. So it's pretty clear that this is at least as big as this, because you have more flexibility. And then we can just say, well, this is going to be at least as large as any value for I that we care, right? So here we're selecting the maximum I, so we can just use I star and plug it in right there if we want. And we know that this statement is still going to be greater than or equal to this one here, right? So it's just, I star was considered up here, and so whatever the max was here was at least as large as I star. And then this is just the value function expression for pi I star, right? And by our definition of I star, that's equal to the max policy value. Right? So you can look at these steps. They're just basic inequality steps. All right. And so that's all there is to that proof. What I wanted to show you one thing that we've done here. This is probably 4 or 5 years ago now, but it was kind of an interesting application of this policy switching. I was working with Eduardo Catilla Sanchez. He's a power systems person here. He does a lot of work in sort of resilience in power systems, and in particular what happens when blackouts start to occur or lines go down. How do you respond in those situations, right? So when things go bad, these are just motivating major blackouts that have happened, right? So you've all heard in the news of these situations where you have these cascading blackouts. And why do those happen? Well, it's because the power system engineers, they're just not fast enough, and their systems aren't smart enough to figure out the best courses of action to sort of react to what's happening. That's one of the issues. Is also sort of the information flow issue as well. But the control is also a huge part of it. And so typically in electrical grids, they have this concept of n-1 stability. It's actually mandated by law. That it's a hard thing for them to mandate, but you can at least do some simulation to verify this. But n-1 security means that if one line goes out like this, then the rest of the network will still be okay, right? Because so you need some level of redundancy or extra capacity in the network for this to sort of happen. But they're mandated to need to make sure the networks satisfy this. But that doesn't say what happens if two lines go out, right? If two lines go out, well, sometimes bad things can happen. So maybe those two lines go out and this line starts getting hot, right? Just the energy flow. and that line goes out. And then this is where these cascading failures happen. Right? They're hard to predict. And what you'd like is to be able to figure out things you could do when these situations are arising to minimize the amount of damage, minimize the amount of blackout, the size of the blackout. And this is an area of power systems research where they'll develop things they call remedial action schemes. And so this is one of these areas where, like I said, it's a competition among researchers to develop policies. My remedial action scheme is more effective than your remedial action scheme, and under different conditions. And there's a whole bunch of different schemes out there. Like one class of techniques is called load shedding. That's basically they shut off parts of the network. That's what happens when your neighborhood loses power. Sometimes they've shut it off, or it was shut off because a line went down. But they can shut off parts of the network to reduce load. Or there's also something called islanding, where they disconnect parts of the network so that they can operate independently. And it's a little more complicated to explain why that helps, but a lot of times that can sort of reduce some of the feedback loops that cause some of this bad behavior. So islanding and load shedding are two major schemes, and there's a whole bunch of sub-policies within each of those. Like with islanding, how do you decide what parts to island? Load shedding, how do you decide what parts to shed and by how much? And so there's all these questions, and that's why there's no way to solve for these things optimally. So that's why there's this whole industry of heuristic policies and whatnot. So it kind of fits this situation that we were talking about. You have all these policies, and you'd like to be able to, do as well as the best policy in the group. Like that sounds pretty good. So you've got all these years of research, and we're going to do as well as any of them using simulation. And of course, this assumes that you have a good enough simulator and that you have a fast enough simulator, which is probably the biggest constraint here. We can talk about that in a moment. But so we had a little paper on this a while back, and basically, we were able to show that you can compete with the best policy in a particular set. To make this practical, so we never deployed this. It would take a huge amount of effort to actually get this deployed. On just getting people convinced that it's going to be okay, that it's going to be reliable, but also the computational side is pretty daunting, right? So electrical grids are pretty expensive to simulate, depending on what fidelity you're simulating them at. So you would have to deal with that. But this is actually a very parallelizable approach too. So that's one thing to remember about these simulation approaches. So if you look at this, this is crazily parallelizable, right? So you can parallelize the simulation of each policy, and even within each policy, you can parallelize those. So they're completely independent. So that's one thing on our side here. And so you would basically be, you need to develop a power system simulation that can basically do one of these fast enough. And then you can use a sort of distribution of computation to get you the rest of the way. So that was one interesting application of this that we've applied in the past. And so at the end of the day, it's an easy way to improve, to use a whole bunch of policies to do pretty well. And there are lots of situations where you come across this. The complexity is independent of the number of actions, because that's sort of dealt with inside the policies themselves. And you can also combine all of these things together. So we talked about policy rollout and policy switching. You can do rollout on top of policy switching if you want. There's lots of variations of these things that you can mix and match. And I do have a library where you can do this very easily. Like you can define a policy switching agent, and then you could do rollout on top of it. Because a policy switching policy is a policy, and so obviously you could do rollout on it. But yeah, these things all add up in computational cost. You're going to be doing more and more simulation each time. So with that, I think we're pretty much done. I would have liked to go over something called approximate policy iteration, where it's another way of using, basically you're using policy rollout to generate training data for classifiers, and you can actually do policy iteration in an approximate sense. But we'll skip that. You can look at the slides if you care about that. But I want to move on to get us thinking about tree search, which is going to be the very last topic. So yeah, so you may have heard about Monte Carlo tree search, and this is the place where we're going to talk about that. So far, what we've done in Monte Carlo plan is we looked at the single state case, and we looked at the case of policy improvement. So you can do something non-trivial. And now we'd like to look at the case where, well, I'd like to get something that could, with no extra information, eventually, if I give it enough time, compute optimal actions. So that's where you get to look at research. Of course, you're never going to be able to run any of these things long enough to get optimal actions, but in theory, yeah, they have some nice properties. And in practice, when you run them with a length of time that's reasonable, you also see pretty good results in a lot of cases. So the thing about rollout and policy switching, even if you run them infinitely long, even if you give them infinite runtime, they're not going to converge to an optimal policy, right? Policy rollout, if you run it infinitely long, so you get perfect estimates of all the Q values, the best you're going to do is you're going to exactly replicate the one-step policy iteration improvement. That's the best you can do. There's no other. That's what it converges to. And policy switching, the best you're going to do is converge to that ideal policy switching policy that does its best as well as the best policy in your set. So that's kind of unsatisfying, right? You're not ever going to do better than these base policies or that one-step improvement. And so now we'd like, at least if we want to get an algorithm, at least if we run it forever, it will return an optimal action. That's sort of the key thing. And we're going to first talk about this algorithm called sparse sampling, which is a pretty simple idea, especially if you've ever seen tree search, like minimax search, heuristic search. And sparse sampling came about around the 90s when there was this open problem that basically said, well, if you have an MDP, are there algorithms that can be near optimal that are their runtimes independent of the size of the state space? Right. So that was just a question that people were curious about. We know that we can solve. We know that we have polynomial time algorithms that scale in terms of the size of the state space, like value iteration or policy iteration, or you can use linear programming. But we don't want them to scale in terms of the size of the state space. And so this was an open problem until the late 90s, and then some folks came around and said that, if you just generalize search trees to MDPs, they can show some theory and things. You can actually end up with an algorithm that's independent of the size of the state space, and we'll talk about that in a bit. But what we're going to be doing, and I'll just show you a picture of this, is effectively at every state of the world, we're going to be building this look-ahead tree, right? And we're going to call this an expectimax tree. Now, because what this tree is going to do is, I'll just give you a little summary. Basically, this tree, if we're at state S, we're going to have actions here that we can choose from. And then for every action, we have a distribution over states that will occur. And then when we're in a state, we have a choice of actions. So you can see that this is, if you're familiar with minimax trees, the minimax trees alternate sort of player 1, player 2, player 1, player 2. These trees alternate. We get to make a move, and then nature gets to make a move, right? And nature makes a move by sampling according to the transition function. And the big difference between this and a minimax style tree is nature in this setting is not adversarial. Nature follows a fixed distribution as opposed to trying to hurt us as much as it can, which is sort of what's happening in a minimax tree. So you can think of it as a game against nature, but it's a non-adversarial game. And so, yeah, so just seeing this, I'm sure you could most of you could figure out how to implement a tree search. But we'll talk about it in a little more detail next time, and we'll talk about how this basic idea had nice theoretical guarantees, but the anytime performance is not good in the sense that what we would like is an algorithm, if we run it for longer and longer, the performance gets better and better. Whereas what happens for sparse sampling is the performance is more like you run it for an hour and the performance will be about the same until you get to an hour, and then it will go up a little bit. And then you run it for another hour. It's not a nice, smooth improvement. And trying to get something that's more anytime, that smoothly improves, that's where we're going to end up with a UCT algorithm, which is one of the more famous Monte Carlo tree search algorithms. So it's a more incremental algorithm. So we'll talk about that next time. And so I think basically I'll send out a note about this, but it looks like basically the quiz will go up to policy switching. So the end of those slides. And so you asked enough questions that you completely get out of the tree search stuff. But hopefully you're interested in this enough to pay attention anyway.